welcome our speaker for today, Joe. So Joe is basically a developer relation engineer for the Algorand Foundation, and as someone that is passionate about blockchain technology, he has a deep understanding of Algorand development and enjoys sharing that passion and knowledge with others. Welcome, Joe, and I would like to now request you to share your screen and take over.
All right, thank you for the great introduction. So today we're going to be going over how to build a dApp, basically we're going to be starting with the very basics of how smart contracts work on Algorand, some of the underlying information that's good to know about Algorand before you start developing. And then I'll be going into how to use our different libraries to actually start building a smart contract, and then integrating that into a web app. So let me share my screen. Okay, so today what we're going to be working with is the two main languages we're going to be working with is Python and JavaScript using Node. So pretty much the repo that we're going to be following here is this github.com/algorand-devrel/beaker-auction. And I'm going to be starting from scratch and basically building out this application. But if you're interested in kind of seeing what the finalized code looks like, you can go here and take a look. But we'll be starting from scratch and kind of walking through how to build the different components. And then before we actually get started with development, I just wanted to give a couple of slide deck presentations, and all the information will be coming from this repository. So this repository is a personal repository that I've been using to develop educational content, and it is something that I've been trying to work on for basically creating open source educational content. So if you have any feedback, feel free to let me know, make an issue on the GitHub, get in touch with me, and that would be much appreciated. So the first thing I'm going to start off with is going over some of the layer 1 features of Algorand. And I opened the wrong file. Okay, so let's open up this presentation. And this is a slide deck about the layer 1 features on Algorand, like the very basic things you should know before you get started development. So right off the bat, first thing I want to mention is, like, why do you want to build an Algorand? I'm passionate about blockchain technology in general, but specifically about Algorand because of a lot of the technical attributes of the chain that makes it a good chain to build on. And at the end of the day, the main reason is it's a good chain for end users. We have around 4-second block time. So this basically means when a transaction happens to change the state of the chain, it occurs in 4 seconds. And the instant finality means after that 4 seconds occurs, it happens right away. We can handle up to about 6,000 transactions per second. For every transaction, there's a 0.001 algo fee. And for those that aren't aware, algo is currently roughly equivalent to around 30 cents in US dollars. So this means fees are like a 40th of a penny or something like that. So the fees are very low. And then, of course, we at Algorand really care about sustainability, and we pride ourselves on our low energy consumption of the chain. And this is kind of one of the things that makes it a great chain to build on, not only right now to build your app, but also long-term, right? How sustainable is it for the environment? And Algorand is a great chain to build on to make your app sustainable. So one of the things that Algorand offers at the layer 1 is called standard assets. And these are basically user-created tokens that are primitive to the blockchain. So on other blockchains, a NFT or a token is essentially a smart contract, whereas in Algorand, the token is baked into the protocol. And so you can easily create tokens with just one command. You don't have to worry about the security of the code behind tokens, and they're very easy to transact between users and interact with in smart contracts. So some of the features that are good to know about these standard assets or these tokens on Algorand is you can call them back. So you can have an address that allows that person to take back the asset. You can have a freeze. So you can basically freeze an asset in a given person's wallet. You have metadata URL. So you can basically point to off-chain data, so like things like images, videos, songs, stuff like that. And then we also have a feature called opting in, which basically means accounts need to opt into an asset and whitelist it before they can actually receive it. So in addition to layer one tokens, Algorand standard assets, we also, of course, have smart contracts, which I'll be focusing on a bit later in the presentation. But the main things to take away for smart contracts is that they have a flat fee. So on other chains, you might see like more complex smart contracts really expensive, right? Like on ETH during the like height of the bull market, it was like $50 to transact an NFT to someone else. Whereas in Algorand, it's consistently that 0.001 fee until we hit congestion. But right now, like I said earlier, we're capable of around 6,000 TPS, and we're averaging like maybe like 20 TPS. So a lot of room for growth, and low fees are something you can always expect when building on Algorand. Smart contracts are Turing complete, which basically means that you can do pretty much anything you can think of with a VM or the Algorand virtual machine. But we do have some hard-coded limitations to keep complexity in check. And this basically means we don't want a single smart contract to take up like a ton of memory or to take a ton of time to execute, so we can maintain that 4-second block time, 6,000 transactions per second. And I'll be talking about this a bit more in depth later on. But one other thing to mention real quick is that blockchain or smart contracts can read and write to the blockchain state. So sending transactions, reading variables, stuff like that. And finally, another great feature on Algorand is state proofs. So state proofs are basically a way to verify the state of Algorand on other chains. So what this basically allows is in the future, other chains can be interoperable with Algorand. And this is a strong path to like the multi-chain future that we at Algorand think is the future of blockchain and this technology. So interoperability is very important, and state proofs are one of the ways to enable that. These are the pretty complex topic. I'm not going to go too in depth. The main takeaway, though, is that Algorand is designed to be interoperable in the future with other chains. Then one other thing worth mentioning, this isn't so much of a feature as just a quality of how you interact with the blockchain, is that every account has what's called a minimum balance requirement. And this basically is the minimum balance the account needs to hold in order to continue participating on the chain. So by default, you need 0.1 algo to be considered a natural account. And then any transaction that results in you going below that amount. So let's say you have 1 algo and you try to send someone 1 algo, that transaction will fail because it puts you below the 0.1 algo. Any transaction that puts you below that amount will basically fail. So the minimum balance requirement is a way to make sure that minimum requirement is always met by any given account. And the minimum balance requirement is used in a couple of different scenarios, which I'll talk about in the next slide. But this is how basically space is rented in the chain. So the current state of the chain, anytime you increase the size of the chain, you need to pay for it with an increase in minimum balance requirement. So these are some of the different actions that one can take. Again, I'm not going to go in too depth on this because I want to focus mostly on smart contracts. By doing things like opting into an asset, opting into an application, creating an application, and opting out, and all of these I'll talk about a bit more in depth in the future. But these are all different things that you do on chain that can increase your minimum balance requirement. And as a developer, this doesn't affect you too much. It's mainly just a good thing to know as an end user, and when you're developing, might be a good thing to check before you send transactions. So also on Algorand, we allow rekeying, and this basically allows one account to sign transactions for another account. And once you rekey an account, it cannot be sent by the original owner. So this is a good way to transfer account to someone else without having to like manually transfer all the algo or all their NFTs and transactions. You can simply rekey the account to another person. And then finally, we have atomic transactions. And this basically means you can group transactions together on Algorand, and those transactions can basically talk to each other and get information from each other in smart contracts. So by default, you're limited to 16 transactions together, but using some smart contract inner transactions, which I'll talk about later, you can send up to a total of 256 atomic transactions. And what's really key here to understand is that with an atomic transaction, if one fails, they all fail. So if you have, right, like one transaction where you're sending a payment and a smart contract that ensures that payment was actually sent, they will fail if one is incorrect. So it's a good way to kind of expand the possibilities of what's doable in a single transaction and kind of form them together to make the interoperability between different transactions more like cohesive, and allows you to do some like really complex design methods, some of which I'll be talking about as we get started with development. So that is the layer 1 features of Algorand and kind of the intro to like Algorand chain as a whole. I know I went through that pretty quick. I could probably talk about Algorand for hours, but we have an hour and a half here. So I'm going through it a little bit quick because I mainly want to focus on smart contract development and get hands-on with that and what that looks like. But before we do that, there's one more presentation that I want to go over real quick, and that is a presentation on smart contracts itself. So we'll be going over kind of the base information about smart contracts itself and what they look like on Algorand. And I see someone asking if they could get access to the slides. Certainly everything is in this repository. They're currently written as Markdown, but if you want to export them to slide decks, you can do that using the npm repository, and I can talk about that if we have time at the end, how to do that. My goal was to have this as like a Google slide and make it like look nice, but I ran into some technical difficulties with doing that. So just working off these very boring slides right now. Okay, so smart contracts. So let's talk a little bit about the underlying tech for smart contracts and what the tech stack looks like. So at the lowest level, we have the Algorand virtual machine. If you're familiar with blockchain development at all, you've probably heard of the Ethereum virtual machine, right? Solidity. Algorand is completely different from that. We're not compatible with EVM, at least not on the layer 1, and we don't support Solidity. So the Algorand virtual machine is basically a portion of the software running on every node in the network that is executing smart contracts. So the AVM is basically the runtime for smart contracts on Algorand. And this is very similar to Ethereum, right? You write your code in Solidity, and then it gets executed in the EVM environment on a node for verification. So like I said, we don't support Solidity, but the native language we do support is called Teal, or Transaction Execution Approval Language. You'll pretty much never see it fully written out like this. It's almost always referred to as Teal, which I'll be referring to it as Teal going forward. But basically, Teal is an assembly-like language for writing smart contracts. And for those that aren't too familiar with assembly, it's a painstaking kind of language where you write one operation per line that either pushes or pops data from a memory stack. And I'm not going to go too in depth on this because working directly in Teal or any assembly-like language is a bit cumbersome. And so we offer some higher level languages to make development a bit easier. And the primary library for that is called PyTeal. And PyTeal is a Python library for writing Algorand smart contracts. And then we have Beaker, which is a framework that makes writing smart contracts even easier and helps you with things like deploying the smart contract, testing it. And it's kind of analogous to, like, you could think of PyTeal as like a web framework or a web server, and then for like writing a very basic application. And then Beaker is a more complete framework. So something like Django or like Ruby on Rails, where it provides a lot of abstraction and helper methods and stuff to make development as easy as possible. But at the end of the day, whether you're building using Teal or Beaker or any other higher level language, everything compiles down to Teal, because that is ultimately the language that the Algorand nodes understand. So a little bit of information about the Algorand virtual machine. So basically information about the runtime that smart contracts are executed in. When a smart contract is being executed, there's some available data that it has. So it has transaction information, so it can see, who sent the transaction, what the fee paid was, what the amount of the transaction was. You can see global variables. So this is stuff like the current round, the latest timestamp. Basically, global variables mean information about the blockchain as a whole. And then you have application state. So this is basically stuff that you can save in one application call and refer to later in another application call. Then, of course, since it's a blockchain, everything's open and transparent. You can use like an indexer or a explorer to read information about applications in a current state. And so, as I mentioned previously, AVM and Teal are Turing complete, meaning really anything is possible given enough memory and time. But we don't have unlimited time and memory, especially when we want to meet those metrics of 6,000 TPS and 4-second block times. So what are the constraints? Like, how do we meet that timing and ensure that any given smart contract doesn't go over that time? So we introduce some constraints. In other chains, the constraint is through gas fees, right? So the most common thing is like on Ethereum, more complex you have, the more expensive it is. So the incentive to not write really complex applications is a monetary one. You don't want to do a super complex application because you could spend hundreds of thousands of dollars just to execute it once. But on Algorand, we have static fees. So how do we limit that? So the way we do it is by hard coding constraints into the AVM itself to reduce computational complexity or to restrain computational complexity. And these restraints are basically restraints on what sort of state the smart contract to execute and how many operations the smart contract could do. And I'll be talking about both of these in a later slide. But it's important to know that the Algorand execution of a smart contract is constrained by hard code rather than being constrained by like monetary incentives. So real quick, there are actually two modes of use for a given smart contract. In general, most of the time we recommend sticking with applications. That's what we're going to be going over with today. That's pretty much what the rest of these slide decks assume we're going to be talking about. But it's worth mentioning real quick, stateless smart contracts, which we call smart signatures. And these are basically like private keys that sign transactions conditionally based on a logic. So you can do things like a delegated approval, which basically lets you, if one end user, let's call her Alice, if Alice signs a delegated approval contract, then that contract can spend money or send transactions on behalf of Alice's account. Then we also have a contract account where it's more traditional, where the smart contract can sign transactions for its specific address. And smart signatures are a little bit confusing, at least they were for me when I first started. But right now, with the state of how much you can do with a stateful application, it's really recommended that you don't bother with smart signatures unless you absolutely need to. But for most cases, you just want to stick with stateful applications. And stateful applications, they have saved state, so they can modify the chain. So you can basically write things to the chain and then later read them. You can log messages to the chain and you can send inner transactions, which basically means you can call an application and then that application can then spin off other transactions, kind of like nested transactions, basically, within the smart contract. So for application state, we have global state, which means there's 64 key value pairs per application, and each key value pair is limited to 128 bytes. So this size limit is per key value pair. So it's the size of the key plus the size of the value has to be 128 bytes. And then we also have local state, which is the same 128 bytes, but we have 16 key value pairs per account. So what this basically means, let's say you have an application with 1,000 users. You would have 64 key value pairs for that application. But then for each of those 1,000 users, you could also have 16 key value pairs per account. So you would have 16,000 key value pairs in total. The caveat with local state is that accounts must opt in. So this goes back to that minimum balance requirement in the opt-in scheme I referred to earlier, where in order for an account to use local state on a smart contract, they basically have to reserve some of their algo to be locked. And again, this is basically a way to rent that space from the blockchain. We can't just let anyone use this space for free, because then we'll run into like a ton of problems with chain growth and like congestion, stuff like that. So accounts have to explicitly opt in order to use this local state, but otherwise applications can use global state freely as they wish. So inter transactions, as I mentioned, they're basically a way for smart contracts to send transactions from within themselves. So a smart contract can call another smart contract. It can send a payment. It can like opt into an asset. It can transfer assets. It can basically do anything a regular person can do when interacting with Algorand blockchain. And again, it can send up to 16 transactions. So if you have a group with 16 app calls that each do 16 inner transactions, you have 256 transactions together. And if one of them fails, they all fail. And so every application, I should mention with inner transactions, all the transactions happening come from a contract specific address. So when you create a application, it gets an ID, which corresponds to the block it was created on. And then it gets an address that is basically a hashed version of that ID. Derivation of that is really important. The main thing to take away is that every application has an app ID, which is used to call the application, and then a contract address, which is used to fund the application and where the application sends transactions from. Then we have logging. So logging is a way to basically write messages to the blockchain, and this is really useful for like returning data. So when you call a smart contract from like an SDK or a front end, for example, there isn't like a native return value. Instead, how returning works is you just read the last log message of the contract, and that is essentially the return value. So logging is really important for like maybe making what the contract is doing transparent, but also for like returning data. So a little bit more about the constraints. So we have an opcode budget, and this basically means every opcode or every operation you do on chain has a cost associated with it. So similar simple operations like addition, subtraction, division, stuff like that, the opcode cost is just 1, so it subtracts 1 from the opcode budget. More complex operations, so stuff like hashing data or like verifying a crypto signature, right? Those are more computationally complex and thus have a higher cost associated with them. And by default, the opcode budget for a given application, I think, is 1,900. And then, like I said, a lot of operations, like most of the simple ones, are just subtract 1. So if you start off with just doing addition, that just subtracts 1 from the 1,900. But you have some more complex stuff that may subtract 50, 100, even some that do 1,000. But the nice thing about budget is that it's pooled for application calls. So if you have a really computationally complex application call, you can add more application calls into the group transaction, and that'll let you ensure that you don't run out of budget. So the other thing that's constrained is state access. So when you call a smart contract, you have to define what sort of state you're reading. So for example, a smart contract can't just get the balance of any given account. You have to specify that account and that you'll be reading the balance when you call a smart contract. And the same applies for applications and assets. So basically, if you're getting asset balance, if you're getting application state, getting account balance, basically anything where you're reading a variable state from the blockchain, you have to predefine what that state is, and you're limited to, I think it's like 4 applications and 4 accounts and 4 assets that you can read from in a given smart contract call. So what does the anatomy of a smart contract call look like? You have your app arrays, which is what I was just talking about, define what sort of state can be accessed. You have an argument array, which defines basically like arguments for the contract itself. So like you can think of if you're defining a function in any given programming language, it has arguments. Same thing with Algorand smart contract. You basically call a function that might have some arguments. And then we have what's called an onComplete. And this is basically the action to take upon execution of the logic. And basically, this different onCompletes, like some examples are like update, whether you want to update the logic, delete it, delete the application, stuff like that. And I think I have a slide more on that a bit later. But so that was for app calls, and then app creation specifically. Of course, when you create an app, you need to define what the logic for the app is. So you define an approval program and a clear program. The approval program is the Teal code that defines what occurs during application calls and application creation. And the clear program is a separate Teal file, so a separate set of logic that defines what happens when someone tries to clear their local state. So if an end user uses a contract, they opt in, they save some things to local state, but they want to opt out, free up that minimum balance requirement, they execute the clear program to clear out that state. And should be mentioned that when you're designing a smart contract with local state, that an end user can execute the clear program at any time. And even if the logic fails, the state will still be wiped. So local state is not guaranteed to be persistent. So that's just something to keep in mind. And then also when you're defining, excuse me, when you are creating an application, you need to define the schema. So by schema, this basically means what the sort of data you're saving in global and local state looks like. So whether you're saving integers or byte arrays, and once you create an application, the schema cannot be updated. So let's say you create an application that saves 1 byte array and 1 integer. If in the future you try to add another integer, it will fail and there's no way to expand that. So this is something when you're designing a contract, it's very important that you think ahead of time what sort of data you're going to be saving. And these are some of the onCompletions that I was talking about earlier. So these are basically things that you can specify the contract to do after the logic executes. So no op is kind of like the standard onComplete that most calls use. This basically means do nothing. So this, you're still executing this contract, so doing whatever the logic says, but after the logic executes, you basically just like return and not do anything else other than what the logic dictates. You have opt-in, which allocates local state for the sender, closeout, which clears the local state, clear state, which calls that clear program to clear the local state, regardless of the logic outcome, and update application to update approval and clear programs. So basically how you update the application, and then delete application, which as you might guess is used to delete the application. And finally, we have what's called the ABI, and this is a standard. So on Algorand, our standards are called ARCs, Algorand request for comment, and this is very similar to ERCs if you're familiar with Ethereum. And the ABI is basically a way to specify method signatures. So like the different methods defining a contract, how do you know what they are? How do you know what to call them? There's an ABI JSON file that defines what those are. Then the ABI also provides a way for higher level languages to use more interesting types aside from uint64 and byte strings, which is the only native type supported by Teal and AVM. So using an AVM or ABI compliant higher level language, which PyTeal and Beaker are, which we'll be using, you can do stuff like different encoded integers. So like uint16, you can use tuples, you can have decimals, you can have Booleans, all sorts of interesting like data types that you might want to use outside of just integers and byte strings. Okay, so hopefully that wasn't too boring, but I think it was good to get the kind of foundational information out of the way before we actually get hands-on. So now we can actually get hands-on with some development. So we're going to be getting started with just Python, and I'm going to be using VS Code here. So I'm going to create a new window and open up a terminal. And with Python, you want to make sure before you get started that you have the right version installed. So if you do a Python -- version, you can see that I have Python 3.10.4 installed. If you're going to be using PyTeal and Beaker, which we're going to be using here, and which is the recommended kind of development path for Algorand, it's important that you have version 3.10 installed. If you have an older version, you won't get the latest versions of PyTeal or Beaker, and you'll be missing out on features. You won't be able to run up-to-date code. You'll run into all sorts of problems. So make sure you're on 3.10 if you're following along, or if you're interested in developing on Algorand using our Python libraries. So once you have Python 3.10 installed, then we can kind of get started and install the necessary dependencies. So the first one is just called PyTeal. So if we do pip install PyTeal, I already have it installed, but this will install the PyTeal package, which again is basically the Python library for writing smart contracts. And then the other module we want to install is called Beaker, and on pip it's labeled as PyTeal -Beaker. So oops, forgot the install. So pip install PyTeal Beaker, or maybe it's Beaker PyTeal. Yep, pip install Beaker PyTeal. I already have it installed, so it's not going to install. It might take a little bit to build the native packages, but Beaker PyTeal and PyTeal are the main two Python modules that you need for actually getting started with development. Okay, so now that we have the requirements out of the way, let's talk about actual development. And please let me know if you need me to zoom in, just let me know. So first, we're going to get started with a very simple contract. Okay, let me zoom in. Let me zoom into the terminal as well. Okay. Let me know if I need to zoom in more. But so getting started, now that we have the packages installed, we can run we can add our imports. So like any other Python package, you run from PyTeal import star to get all the imports from PyTeal. And let me zoom in a little bit more. And so from PyTeal import star to import the PyTeal packages. And we're also going to do from Beaker import star to import all of our Beaker packages. But before we get started, let's just briefly go over like what a very general smart contract looks like with PyTeal, kind of how PyTeal works, just at a very, very basic level. So the first thing we're going to do is we're going to write the classic hello world that you do when getting started with any language. So what we're going to do is we're going to define a function called approval program. It's not going to take in any arguments. And this is how we're going to organize our code for the approval program. Again, the approval program is basically the logic that is executing when someone calls or creates the contract. So the first thing we're going to do here, we're going to type return seek. And what this seek is it stands for sequence. And in PyTeal, basically every sort of method that's provided by PyTeal, or most methods provided by PyTeal, return what's called a PyTeal expression. And so the PyTeal expression is ultimately what converts to that low-level Teal opcode. So basically, the PyTeal expression tells the library what we want to do at the low level of Teal. I just realized that I am not in a directory here, so let me enter. Yeah, move. Okay. Gotta zoom in again. Okay, sorry about that. So what this does is, let me zoom out. One more. Okay. So what this does is basically tells us what the sequence of things we want to compile are for our resulting contract. So what we want to do here is we're just going to log the string hello bytes. So we're going to use this log method, and then we're going to pass it a string of bytes. So you might notice that we explicitly defined bytes here. So instead of doing, log hello world, we're doing log bytes. And the reason we're doing that is because the AVM itself in Teal, the native type it supports is byte arrays. And so if we were to just pass a string, PyTeal and thus Teal don't really know what to do with a Python string. We need to specify that we're working with a byte array for Teal, and thus we're using this bytes method. Then what we're going to do is simply return from our contract. And when returning from a contract, if there is a non-zero value that we're returning, that's considered a pass, which basically means the smart contract will execute and do whatever the logic says it will do. And now we're just going to write essentially just like a helper function for printing out this data. So we're going to do compile Teal. So that basically means take in a method and then convert it to Teal, giving it our approval program. Oh, my copilot automatically filled this in for me. So we are just doing print compile Teal, passing in the approval program, specifying that we're compiling an application. Our version here will specify version 6 because that is the latest version that is released on mainnet. So now that we have this, what we can do is execute Python contract py. As you can see, it prints out this assembly-like language, which is called Teal, and that is the logic for a smart contract. So to recap, PyTeal in general, you work with what are called expressions in every function, such as log, bytes, int, return. These all return expressions in PyTeal. And just compile Teal basically reads in those expressions and converts them to Teal. And the sequence is essentially a way to define a sequence of multiple expressions. In our case, this log expression followed by this return expression, and then ultimately compile it down to this assembly-like language, which, as you can see here, does byte hello world, which pushes this byte string into the memory stack. It calls log, which reads the memory stack and then logs it on chain. And then it pushes the integer 1 to the memory stack and then calls return. And since we have a 1 on the memory stack, it's considered a successful execution. So the contract would execute. So that's the very basic overview of how like PyTeal works. And now we can actually get started with building out our application. So the application, as I mentioned in the very beginning, that we're going to be building out is going to be an auction application. So I see someone asking what dApp stands for. So great question. Probably should have started there. So dApp stands for decentralized application. So in the context of blockchain, this basically means you have a portion of your application that is decentralized. So when you're building on Algorand, there's a portion of your application that's using Algorand transactions and using Algorand transactions and smart contracts to execute some logic. So it's not sitting on a centralized server anywhere. You're having logic being done on chain that's going through the decentralized consensus mechanism of the blockchain itself. So dApp is basically integration of like a front end. So we'll be using a web-based browser for our front end, and then decentralized logic, thus our smart contract. So for our auction dApp, so a decentralized auction application, we can start defining what kind of the overall architecture is going to be. The first thing I like to do is just kind of write out pseudocode for what we're going to be saving. So in our global state, we're going to have a couple things. We're going to, first, we want to specify the owner. So who the owner of the current thing being auctioned is. And this is going to be an address. And then we also want to have the highest bidder. So it's also going to be an address, and this is going to be the person that currently has the highest bid. We're going to also have the highest bid. So this is essentially the amount that the previous highest bid was and what the amount that the new bid has to beat. And then finally, we want to specify the end of the bid. So when does the auction end? And this is going to be an integer that basically maps to a timestamp for when the auction should end. So like I mentioned, it's important that you define what sort of bytes and what sort of integers you're going to be saving. As you can see here, we have 2 global bytes. So that's our owner and our address. And we have 2 global ints, and that's our bid end and highest bid. And that's important to know for when we define our contract. But for now, we'll just leave these comments here as kind of our framework that we'll be building on. So in terms of what sort of functions we want. So first, we want a function that creates the contract. So basically create the auction contract. So when we call this, we want to set up our global state and basically initialize everything so that we're ready to run auctions. So the other function we want is something to start the auction. So once we have the application creation, how do we signify that we want the auction to start? The other thing is a function to end the auction, which actually we're not going to go over today. So we're going to leave that at the bottom there. But basically, we're going to want to have, as you build this out, you would want to have functionality to say, okay, what happens once the auction is over and you need to change who the current owner of the item in question is. So one function we definitely want is bid. So basically the logic for handling what incoming bids look like and how they should be handled. So think of, what happens if the bid isn't enough, what happens if the bid is the same person, stuff like that. So these are kind of the main functions that we're going to be working with. And the first thing we do when we're making a application, so here we're going to be using Beaker, we're going to actually make this a class. So if you're not familiar with Python, to define a class, we just do class, the name of the class we want it to be. So I'm going to do auction. And then we want to specify what we're inheriting the class from. So we're going to be inheriting it from application, and this is from Beaker. And so what this is basically doing is we're saying we're creating a Beaker application called auction, and then we could start defining our global state and our functionality here. So for defining global states, we're defining properties of the Python class. So what that looks like is specifying For example, now let me move this down here so we can keep everything in line. So we can specify owner, and we're going to set that equal to what's called an application state value. And so what this is basically doing is are basically saying we want this owner property to map to an application state value in our contract. So one of the things we want to also specify is on this application state value, specify the stack type, which is basically what kind of data are we saving in here. And this is going to be bytes. So again, this is a global byte. It's going to be an address. So we're going to specify application state value. This is saving a Teal type of bytes. And we're going to do the same thing here for address. Okay, so sorry, confused myself there. We're not, the name of the variable is an address, it's highest bidder, which is in turn address, which is a Teal type dot bytes. So that's basically what we're doing here, is we're telling Beaker what our global state is going to be, and it can see that we have 2 bytes, owner and highest bidder. And we're going to do the same exact thing over for our integers. So copy this code over, and instead we're going to do highest bid. Just realized I lost my chat window, so I'm just going to pull that up. Okay, so we're going to have our highest bid, and we're just going to change this to uint 64. And we're going to do the same thing for bid end. And specify uint 64. Okay, so what do we have right now? So we have a smart contract that we know we're going to have 2 global bytes, owner and highest bidder, and 2 integers that we're saving in our global state, highest bid and bid end. So now let's talk about what we want to do for the logic upon creating a contract, or upon creating this contract. So we're going to do def create, and we're going to specify self here. And then we're going to return a sequence, much like we did, for that hello world. So we can do return seek, and then, what we can do here is we're going to just basically set up our global state. So we're going to do self.owner.set. So set is a method for updating global state value. So here owner is an application state value, and we want to set it to a new value. In this case, we're initializing it, and we're going to initialize it as the person that is creating the application. So that will be the person that is sending this transaction. So that'll be self.owner.set, and to get the transaction sender, we're going to do txn.sender. This txn method has a ton of different methods on it. Generally, it's a way to get information about the current transaction, but here what we care about is just the current sender. An important thing to note, like I said, pretty much everything returns a Pi2 expression. So if you note here, we're not doing txn.sender as a property, we're calling a function, and that's really important. That's something that's really easy to trip up on, and you get all sorts of errors if you don't call this function. You need to call this function because this is a function that returns the Pi2 expression. And then we're going to do the same thing with our other global state variables. So here we're just going to set the highest bidder to an empty string, since when we're first creating the application, no bids have occurred yet. And we're going to do self.highest bid. We're going to set that to 0. Self.bidEnd, we're going to set that to 0 as well. And one thing I should mention, you might see some autocomplete that's happening. And this is because I have GitHub Copilot installed, which is basically like a AI autocomplete thing that you can integrate with VS Code. So if you're interested in that, that's not something that natively happens with like the Algorand extension. That's something specific to GitHub Copilot. And if you're interested in that, I recommend checking it out. If you just Google GitHub Copilot, I think you get a year for free. And as you can tell, like when I start typing stuff, it'll basically suggest what it's doing. Basically suggest like what it thinks you're typing. So that's really helpful for like development and making it quick and easy. And as you can imagine, like Algorand development is pretty niche, but even with this like niche tool set, it's been really helpful. So kind of just of a side note there, if you're trying to be as effective as possible, look into Copilot or maybe some other AI assistants for development. Okay, so we have our create method now. And the one thing we want to do here is add a decorator to tell Beaker that this is the method we're going to call when the application is created. So we're just going to add this at create decorator. Excuse me, excuse me, my throat keeps drying up. But anyway, so this create decorator tells Beaker that this is the function that we're going to call when the application is created. And I'll explain a little bit more about why that's important when we start to get into integration with the front end. So basically, how that looks like is we have this create function, and then when we deploy our application, we can then just call application.create, and it will automatically know that this is the logic we're talking about. Okay, so we have that create out of the way, pretty straightforward logic. Now let's get into something a little bit more complex that's going to take in some arguments, and that's going to be the start auction function. So we're going to do self auction self, but this time we're going to be defining some arguments. So before we actually do that, let's just write down the things we want to do. So the first thing we want to do is we want to fund the contract. And the reason we want to do this is, like I mentioned, any account has a minimum balance requirement in order to be considered a valid account on Algorand. And so we have to fund the contract with that amount in order for that account to be active. So we have to fund it with 100,000 microalgos. And I'll talk about how we make sure we do that as we go on here. And then we also need to make sure that we set the bid end to whatever time is specified. So we'll be taking in a length of the auction, and then setting that to the end of the auction. And then finally, we'll have a check, or basically an input that signifies to the contract what the starting bid should be. So set up a starting bid amount. Okay, so let's first, again, we're going to be using a sequence. So we're going to return seek. First thing we want to do is verify that we have a fund transaction going to the smart contract. So what we need to do first is take a payment as an argument. So here we're going to use the ABI specification. So as I mentioned, the ABI is a way to define how a method should be called. And what we're going to do here is specify a payment arg, and this is going to be an ABI dot payment transaction. So what we're doing is we're essentially going to assert that or actually first, once we get this payment, just going to do payment.get, actually get the value of that transaction. And then here in our assertion, we're going to assert that payment dot receiver is equal to global dot current application address. Okay, so what is this doing? So what this is basically doing is saying, okay, when we call this contract, one of the arguments to this method is going to be a payment transaction. And so we're going to get that payment transaction, and then we're going to verify that the receiver of the payment is the application address of this current application. So what we're basically doing is we're checking, is there a payment being made to this contract? The next thing we want to do, as my co-pilot is suggesting here, is we want to verify that the payment amount is the 100,000 microalgos. That is the minimum balance requirement. So we have those two assertions for verifying that the contract is indeed getting funded. So we have this checked off, put that here so we can organize. And next thing we want to do is set the bid end. So to do this, we're going to do a self.bit.set, and we're going to send it to, or set it to global, the latest timestamp. So what this does is basically gets the latest timestamp for the last block that it was approved. So this is kind of a way to get time in your smart contracts, but it should be noted that since it's a decentralized system, timestamps can kind of not necessarily align with wall clocks. So it's not super accurate. Like if you need timing down to the second, you would need like an external service to provide that. But just on-chain, global.latest timestamp is a good way to roughly get what time it is during time of execution. And then we're going to be reading from length. It's going to be you went 64. And so what we're going to do is get our latest timestamp and then add the length of the contract, so, or the length of the auction. So what this is doing is basically setting this bid end to the latest timestamp plus this offset. So if we specify the length to be a day, this will basically mean the auction will end in a day, given this logic. And finally, what we want to do is set the highest bid to the starting price. So we have a starting price.get. And again, we're going to go up here. Starting price is going to be UN64. So summarize this, we have a start auction call with a payment as an argument, a length as an argument, and start price as an argument. And then we are setting our global state as appropriate. So why is this global state plus gain? Oh, I think we have an extra, extra parentheses there. There we go. So what we're doing is we're basically making sure that we're funding the contract with a payment of 100,000 microalgos, which, so the native asset on Algorand is algo. Microalgo is 1 times 10 to the negative 6 algos. And when you're working with smart contracts, you're working in that smaller microalgo unit. So this equates to 0.1 algo or 100,000 microalgo. So in the start auction, we got our payment, our length, the starting price, and we use that to set the global state accordingly. And then finally, we're going to set up our bid functionality. And I'm running a little tight on schedule. So, one thing I need to mention is that we need to add this decorator here, this external decorator. And this basically means that this is a function that can be called from off-chain to on-chain. So basically telling Beaker that this is a function that we want to call through the API method that I specified earlier, right? Basically, this is a way to advertise, hey, start auction is a call that, or is a method that we want other people to be able to call. And we do that through this external decorator here. Okay, so finally, we have our bid. And since I'm running a little bit low on time, I want to make sure I have enough time to go over the JavaScript integration as well. I'm actually going to be copying code from the speaker Teal library. So again, if you want to see the complete the complete code base that we're going to be working with, it's all right here. Algorand DevRel speaker auction. I'm just going to be copying some code here and walking through it just to save some time, so I make sure we have enough time to go over to go over the JavaScript integration as well. So what this is doing, much like our start auction method, we have a bid method that takes in a payment, but of course this payment this time around is going to be the actual bid itself. And then I just write set these variables just to make it a little bit easier, so I don't have to write self-auction get every time. So basically, what we're doing here is we're going to first make sure that we're not at the end of the auction. So we're going to check that our global latest timestamp is prior to the end of the auction that we set in the start auction function. So this is basically ensuring that no one can bid on it after the auction has ended, because we don't want people sending their money here if it's worthless. And then we want to verify the payment transaction. So much like we did before, where we verified the amount in the sender or the amount in the receiver, here we're verifying the sender and the payment amount. So we're going to assert that the payment amount for the bid itself is greater than the highest bid. So we want to make sure that whoever's bidding currently, they're bidding higher than the previous bidder. So that way they become the new highest bidder. And then we're also going to assert that the sender of this transaction, so we see TXN, that basically means this application call. We're verifying that the person that called the application through txn.sender is the same as the person that sent the payment. Then now we have some conditional logic for sending back the previous bid, which I'll talk about in a second. And then finally, we're going to update our global state. So we're going to set the new highest bid to whatever the amount of our payment was. So again, the payment is the bid transaction that we get as an argument. And then the highest bidder, this is going to be the person that sent the bid. And we're going to update that global state to point to their address. Okay, so let's talk about this conditional logic right here. So what this conditional logic does, before I do that, one thing I should mention is what this assert does is, if you're familiar with assertions in other languages, it basically says, is the statement true? If not, fail. So if this assertion were to fail, right, if the highest bid was lower, or if the highest bid was greater than the current bid, then it would fail. A smart contract call wouldn't go through. The transaction would get rejected. So that's what we're doing with assertions here. So here we have the conditional logic. So here we're checking, is the highest bidder an empty byte string? So what this basically is doing is checking, has there been a previous bidder? If so, we're going to execute this argument here. So we're going to execute this self.pay method, which I will define in a second. And if not, we're not going to do anything. Normally with if statements, you would have the else statement here, but we're not going to have an else statement. So we're just doing, if the highest bidder is not empty, then we're going to execute this pay method. So we need to define this pay method. And the reason we need to define this is because when we get a new bid, that bid is sent to the contract amount. Let me put the link for the GitHub in the chat here. Everyone, okay. So that's the link if you want to follow along. So so when a new bid comes in, you have this problem where the last person's bid is still sitting in the contract account. And obviously, if that person doesn't win the bid, we want to make sure that they get their money back, right? You don't want to just send money to an auction and just have it disappear if you don't win the auction. So what we're going to do here is define a method called pay. Again, copy and pasting code just for the sake of time here. And what this does is executes an inner transaction. So we have this internal decorator that specify this isn't a function that an external user or basically an end user is going to be calling. It's basically a helper method that we're using in our own contract. So we're doing, instead of external, we're doing internal. We're defining the return type to be none. So that's what that's all about. And then we're going to be basically taking a receiver, which is a Pi2 expression, an amount, which is a Pi2 expression, and we're going to be executing an inner transaction. So inner transactions basically look like this. You do inner transaction begin to signify that you're going to start defining an inner transaction. Inner transaction builder.set fields to define kind of the fields of the transaction itself. So here we have tx and field typing them, and that's basically specifying what the type of the transaction will be. So this will be a payment, who the receiver is. So this will be the receiver argument, what the amount is. So the amount argument, and the fee here. This is an important thing to note. The fee we're setting to 0. And the reason to do this is because if during congestion, if we ever receive, during congestion, if we ever run into a scenario where fees increase, you don't want your smart contract to accidentally get drained by high fees. So you set the fee to 0. So the end user, well, how it works is basically if you're sending a group transaction, the one transaction can pay the fees for another. So instead of sending the default fee, you can send double the default fee to cover this inner fee. So once you have that inner transaction set, then you do inner transaction.submit, and that'll then kick off the transaction and actually send it. Okay, so that is the logic for our function, or for our smart contract. Obviously, this is not a complete auction. We would need the end auction, but for time's sake, we're not going to go over everything in detail. So let me hide this. So one last thing that we can do here to take a look at what the compilation looks like is I'm going to define, it's basically this script. Also going to need some imports as well. And basically here what we do is we're going to be basically defining our app and then writing out all the Teal files that it generates. So we're writing our approval program to approval.teal, clear program to clear.teal, our ABI on JSON spec. So this defines what the contract looks like, and I'll show you what this looks like to ABI.json. Then our Beaker application spec, and this is useful for generating front-end integration code, which I'll again go over afterwards. If I do Python 3 contract.py, has no okay, so it is complaining about oxygen. Oh, I have it as okay. So let me make sure. And place. Okay. Okay, so now that I run that, what that does is basically generates all these files. So first of which is the ABI JSON spec. And so this is the file that defines how a person would call the contract. So here you see we have methods. We have this bid method that takes in these two arguments, or that takes in this argument that's a payment. We have a start auction that takes in a payment, length, and start price. and these return void. So this is basically a way that we can kind of advertise how to interact with the smart contract. And then we have our appspec.json. This is not something you really need to manually look at, but it's basically defines how the application is deployed and how it's interacted with. And then we have our approval.teal and clear.teal programs for defining the teal logic that was generated by our PyTeal. Okay, so now the next step, we have our smart contract code and we want to integrate into a front end. So what we can do is if we go to github.com/Algorand devrel, and we have this algo web template. Let me be preemptive here and share this message, share this link. So this is a web template. If you're just starting a project, you can use this project. But what we're going to do here, do git clone algo web template. I'm just going to rename it to web. And then if I go to this directory here, we already have basically some of the startings of an Algorand web project. So if I do npm run serve, you can see that here we have a very simple SDK loading. And if that loads, then we know we will, oh yes, increase browser text. If we have that, then we know we are good to go in terms of development. So again, I know I did that pretty quick. Hold on. So what that looks like is we cloned that algo web template, went to this web directory, ran npm to initialize all the dependencies, and then ran npm run serve to basically serve this web page. So from here, what we can do is we're going to add something called beaker TS. So if I do npmi beaker TS, this is a essentially a tool for a tool for generating a TypeScript interface for a given beaker contract. So what this looks like is, give me 1 second. So what this looks like is if I were to run npx, so beaker, and then want to specify the appspec.json, then I want it to compile and source .beaker. Oh, npm beaker. Oh, beaker source beaker. Okay. Again, so run this npx beaker generate, give it the APIs, the app spec, and the folder we want to generate to. If you go over here and look at our source, we now have basically this library that we can use to write our question for, or write our contracts logic for interacting with the contract in our front end. So I'm running a little bit behind time than I would have ideally liked. So what I'm going to do from this point is I'm going to open up this this existing repository that already has this code written, and I'm just going to walk through it rather than hand typing it. So let me close out all the windows I had open. Okay, so the first thing is just like I just showed. Here we have our Beaker TypeScript file defined here. And this exposes a class that we can then interact with. So if we look at our index.html, what we basically have is a button, actually, let me just run serve. Oh, cd web and run serve. Okay, so this is what the front end will look like. So as you can see, we have a drop-down menu for selecting account, a button to connect account, a button for sending the create, the amount we can specify, and then start bid and end bid. So that's the raw HTML. So what our JavaScript looks like, and if you're a Web 2 developer, you're probably cringing at how terrible this this looks. I'm not a Web 2 developer, so this is very basic, just HTML and JavaScript. But basically, what we do here is we import the auction from our Beaker auction client, right? So if I were to open this, you see we export auction. In our index here, we're importing that auction class. And then in this web template, we also have this wallets.myalgo. For some context, myalgo is a web-based wallet that you can use to send and sign transactions, view your current balance, stuff like that. Then here we're just initializing the session with this wallet. We're initializing a connection to the Algorand node. So here we're connecting to testnet API algonode.cloud. This is a public API service that lets us connect to the Algorand testnet and send transactions to testnet. And then here we're just basically connecting up our HTML and JavaScript. So we're running through, if we look at our HTML, all of our buttons have unique IDs. So we're connecting to those elements and saving them, or connecting to those buttons, saving them, and we're also connecting to our drop-down menus as well. So, and then finally, we're connecting to those buttons here. So we're getting our buttons. Again, I know I'm going through this pretty quick. If you're familiar with Web 2 development, this shouldn't be too foreign to you. If not, I apologize for going through this kind of quick. I want to make sure we meet the time here. So this function I'll talk about in a second. But basically, the first thing we're going to do is define what we do when we click the connect button. So here, buttons connect on click. We're going to do myalgo get accounts. We're going to enable the create account, and then we're going to add the accounts to the button. So if I go over here, let me close this out. So if I go over here and I do connect, it'll come up with myalgo. And if you don't already have accounts, you have to make an account on wallet.myalgo.com and then fund it with a dispenser. But basically, you connect your accounts. And as you can see, I have two accounts, Alice and Bob. And then now that gives us the create option. So taking a look at what create does. Create is where we're interacting with this auction class. So again, this is the class that was automatically generated in this auction client.ts from Beaker. What we're doing is we're telling it the client to use to interact with the blockchain is going to be this algod client that we specified here. And then we're going to be passing this signer function. So what the signer function does is it basically takes in some transactions and then returns the raw byte arrays for those transactions. This is one of those things where the transactions by default, this signed transactions returns like JavaScript objects. So like an object with properties that you can call. And then here we're just converting those objects into just integer arrays. So at the end, our sender function takes in an array of transactions and then returns an array uint8 array, which is basically just raw binary data. Okay, so for our create, we're going to use that to sign transactions. And then our sender, we're just going to get from that drop-down menu. And then we can run through this auction app. So here we do await.auctionapp.create, and that will trigger this signer function and then send the auction to testnet. So here, if I walk through that, oops, you do create. It'll ask me to sign because it called that signer function. And it will take a second to load. I'm gonna wait here. And as you can see, we now have our application created. And this is Algo Explorer. This is basically a blockchain explorer where you can see information about any given transaction or application. So you can see here our schema that we defined, the fact that it's not deleted, who created it, and then importantly here, our global state. So we can see auction end 0, highest bidder 0, highest bidder 0, and then our owner. Okay, so now if we go back, close out these just so we don't get confused here. Nope, I think accidentally closed the wrong tab. So let me just do this again. Great. Okay, so while that's running off in the background, what we can do here is then I'll look at our okay. Yeah, so I'll make the font bigger next time I open it. Okay, so if I go over here, I'm looking at the wrong VS Code. That would explain it. Okay, so I can see, oops, I have this mixed up here, which is why it wasn't working. So our create, disable true, start. Okay, no, that was right. Okay, so for some reason our start button isn't showing. Okay, so anyways, I'll just walk through this transaction logic here. So we run through the create on create on click, and that'll basically take this auction, call.create on it, and then send that to the transaction, to the testnet as we just saw. And then we'll have this start button. And what this will do is, again, it will initialize this app, but this time we're specifying our app ID. And it will, first we initialize this payment here. So the key thing to take away here is we have this suggested parameters, and this basically just means what's the suggested fee and some other parameters that are important to transactions that we should be using here. Then we specify the amount, who it's from. So it's going to be from whatever account was selected in the drop-down menu to, it's going to be to the application address. So if I go back to our web app, I connect. I'm not sure how to zoom in on this. Yeah, so basically what this is it's just an interface for for selecting which wallets you want to connect. So when I connect, I can select Alice here, and it'll tell me the address and the balance. And when I connect to Bob here, it will also tell me the address and their balance here. There we go. Okay, so great, thank you. This interface is basically a way to select what accounts do we want to use to interact with this application. And then when we do the create, what we see here is this transaction that we're sending. So this is the application create transaction, tells us information about the create transaction that we're sending, and then we type in our password here and send it. So now, once we have the create, we now have the start auction. So we can define our starting bid amount will be 10,000. So if I do start auction, again, we're going to see that we're sending a transaction, and what we're exactly doing in that transaction is specified by the logic. And if we execute that here, wait for this to go through. Pull up our console to make sure nothing fails. Okay, great. So we see that that transaction went through. So now if we look at our application, so if you remember before looking at our global state, we had these all 0. So now you can see we have an auction end time specified. We have a highest bid specified, and we currently don't have, but we currently don't have a highest bidder because we just created the auction. And what this basically allows us to do is see what the current state is. So when we create the auction, it sets the highest bid to whatever amount we set, but there is no highest bidder because the auction was just created. And then we have our auction end, which is timestamp in seconds. So now finally, our bid auction, and I know we're running out of time here, so real quick, what this bid is very similar to the start auction. What we're doing is initializing our auction app and then doing a payment, except instead of this time, we're sending a payment that corresponds to the amount defined in our front end, and then we're sending a bid auction with a payment as argument. So looking here, let me change this bid amount to 20,000, do bid. Again, we'll see transfer algo. You'll see 0.02, which corresponds to 20,000 micro algo. Send this transaction and wait for it to go through. Should be a couple of seconds. And then refresh here. See 11 seconds ago, the transaction that just happened. And now we look and we have a new highest bidder defined and a new highest bid amount. So I know I went through the end bit of that a little bit quickly. Ideally, I would have liked to do a little bit more hands-on coding. But hopefully that gives you a good idea, at least, at the very least, an idea of what the tools are like to build on Algorand and what some integration might look like for a contract written using Beaker and PyTeal with a TypeScript front end. If you have any additional questions, I encourage you to reach out to me. My email is joe@algorand.foundation. I'm on Twitter, joe_Polny. And also, if you're not already on the Algorand Discord and you're interested in Algorand development, be sure to join the Discord. I will put the link in the chat right now. And the Algorand Discord is a great way to get in touch with people like myself that work for the foundation or the Inc., or just really smart people that are building an Algorand that are able to support you. So that's everything that I have to go over. Again, don't hesitate to reach out. I am more than happy to help you out. And yes, I will be pasting contact info in the chat as well.
Great. Thank you, Joe, for the amazing session. We'll be posting the recording for this session on our YouTube channel, and you can connect on our Slack for more information about how to reach out to Joe. And you can drop in your doubts even at our Slack general channels, and our community can help you with them. Yeah. Thank you all for joining in. Thank you, Joe, for having this all over.
Yeah, thank you everyone for joining in, and this was great. And